Alrighty, everybody. Thank you for coming. As always, if you would like to follow along this week, we're going to have all of our slides and coding demos posted up in the asset cluster, bit.ly/ACM underscore AI underscore 23F underscore beginner or BEG underscore cluster. With that being said, we're going to get started right here. First of all, a little plug. We have a bit of a course planning social this Saturday. It's from 11 a.m. to 12 p.m. in Engineering 6 289. Also, if you're interested, right after we do our course planning social, that is when we have our reading group. This week is about, I forget exactly the topic. It's something about cybersecurity and AI. So it's a little bit of a collab with ACM Cyber there. And we'd love to see you guys all out there. So, and then also here are all the links, Discord, Instagram, you guys know the drill. So I'm gonna hand it over to Eric.
All right, folks. I know it's like midterms week and y'all got like midterms and stuff. So today's like lesson, like the slides are gonna have like a bunch of math and stuff. Like we don't really require you to like know any math like coming into this. So like it may look really overwhelming, and that's because it kind of is, but just try to like understand the bigger picture of things. If you want to understand the more technical side, like you can come down and ask me after the like workshop today, but we're just trying to get like a conceptual understanding of what's going on. And so we don't really expect you to like know any like linear algebra or anything coming in. But yeah, this is going to be pretty high level, but we are going to be like putting the formulas and stuff up. So just a heads up. All right. But anyways, today we're going to be covering this idea called logistic regression. And like 2-3 weeks, whatever ago, we covered this other idea called linear regression, which helped us essentially build models that could predict continuous data in the future. But the reality is not all data is continuous. And so today we're going to be building models for data that isn't continuous. So here's our motivation right here. So for instance, like I just said, linear regression predicts continuous data. So if you don't remember what continuous data is, all good. Continuous just simply refers to the idea that like your data can be represented with like infinitesimal amounts of precision. So you can sort of think about like a temperature, right? Like to us, all we care about is like, oh, it's 72 degrees, right? To like a digital thermometer, maybe they prefer a little more precision, they maybe want like 72.1 degrees, right? Maybe if you're like looking at like astrological like weather patterns or whatever, maybe you want like 300 decimal points, right? The idea with continuous data is you can take however precise data you want, and like that's just like allowed, So an example of linear regression could be maybe if you made a model that predicted house prices, right? Like you input into your model like a starting price, and then you tell your model how much are houses going to cost in like 10 years, And then the model can predict that, and it's a quantitative value. There's like a cent precision and all that. That's an example of precision or continuous data. But the reality, right, is that not all data is continuous, right? So cool, I can make a model that can like predict house prices, right? But like, what if I want a model that like identified like if I like inputted an image, like which images have cats in them and which images have dogs, Then our continuous model like doesn't know what to do anymore, right? It just throws its hands up. It's like, that's not my job, right? So the idea today with logistic regression is we're gonna be making models that doesn't necessarily like predict quantitative data, but rather categorizes data. So like the slide says up there, we're going to be building models that when given input can categorize things into, I guess, like this or that. So like you give me an image, I can tell, okay, is this a cat? Is this a dog? So yeah, that's sort of the motivation for today. And just a heads up, like if you guys like have any questions or anything, please feel free to ask. This is the beginner's track. We're all trying to live and learn, but yeah. Anyways, so given that, let's start off with we'll start off with a little debrief here. I got some problems, right? It's midterms week. It's rough out here, right? What's going on? I'm not entirely sure whether I want to go to lecture tomorrow, right? I'm kind of like on the fence. I don't know what I'm feeling, This is what I'm thinking, right? So tomorrow, right, like the weather, like I heard it's gonna be like all rainy and stuff, like my next class is gonna be at like 8 in the morning. Like I kind of don't want to wake up for that. And, it's like midterms week. Like I gotta like study, I've been like spending all my time studying. Like I haven't been eating. I haven't been doing well in my midterms. So like every time my parents call, like I tell them like, yeah, haha, yeah. And then I haven't been getting like any sleep, like I don't know, man. So like given this data here, right? Like, do I want to go to class tomorrow? Like what am I leaning towards, like based on this data, right? What are we thinking? Can I get hands up for yes, go to class? Can I get hands up for no? That's what we like to, I mean, wait, this is recorded. ACM does not support like not going to class. But yeah, correct. No, I'm not going to class. And as an out-of-state student, that's kind of tough because it's like 60K tuition, but whatever floats your boat. But essentially, right? Breaking down this big picture here, right? We have some inputted data, right? And based on that, we sort of figured out that like I'm not going to go to class tomorrow, given our inputted data. So you could, I guess, say that the probability of me going to class tomorrow, based on the data, is less than 50%. Fair enough. It's not looking too good, right? All right. Anyways, so if I'm not going to class tomorrow, right, and I'm starving, right, where am I going to eat? These are like the ethical dilemmas that we're facing every day, right? Let's take a look at the data, right? Let's see what's up. So, number one, I'm hungry, right? I need to eat, right? Number two, I'm craving pizza, right? So we're like looking at our data here, right? These are our inputs, right? So I want some pizza, right? And I'm not trying to wait, So those people who want epicuria, not on my watch. I'm not waiting that line because I'm hungry and I want to eat now, right? And given that, let's say like I'm currently in the sprawl area, right? And I'm not trying to climb those death stairs because I lived in Hedrick Hall last year and I'm not running that back again, right? So given all this inputted data, right? How do you, I guess, break down like what my preference is? Which dining hall am I leaning towards, right? If you want to look at it from a quantitative side, right? Maybe you could, first things first, you look at your options, right? We got like 9 options, right? It used to be like, apparently they're opening up like this like acai place next year. So like whoever's doing the workshops next quarter is going to have to update the slides, haha. But right now we only got 9 options, right? And like given our inputted data, right? If you look at it from a quantitative side, you could probably argue, right, that there's like a certain percentage or a likelihood that I go to each of these dining halls based on like what I'm feeling, So given that I'm looking for pizza, I'm not trying to wait, I'm not trying to go up the death stairs, right? Denev's not looking that bad right now, right? Because it's just sort of checking off all the boxes, right? But as you can see, like dining halls that sort of fit some of my data, they're also pretty high up there too. Like Epicuria, we got Ronde, but like Ronde's up the death stairs, right? So that's why it's not like 30, right? And then on the bottom, as you can see, we got like the Dre, we got Feast. Those are like, those don't got pizza, those got long lines, like these are very far from like what I'd like to prefer or where I'd like to go, right? You're probably thinking at this point, like I came here to like learn about AI, like what is this guy talking about, right? Here's where I'm going, right? The idea with logistic models, right? And the idea that we input something into a model and it breaks it down into categories. There's essentially 2 different kinds of logistic regression models. So in one model called binary classification, regardless of whatever you input into it, its output is always going to be 2 things. So most of the time it's like yes or no. So for instance, it's like, am I going to lecture? I either am or I'm not. That's an example of a binary classification. But there's also a different kind of logistic regression model called multiple category classification. So in this instance, we're not limited only to, I guess, like 2 outputs. We're limited to like however many we want, right? So for example, with like me picking a dining hall, there's like 9 different dining halls. Given my input, what I'm feeling, right? I can get a likelihood for like which dining hall I'm really feeling like that night, right? And out of like 9 options, right? Based on my preferences, I'm categorizing which dining hall I feel like would match my preferences the most, if that makes sense. But generally, like in terms of logistic models, these tends to be used for image classification purposes. So let's talk applications here for a second here. So images or image classifications, you've probably seen it everywhere, or maybe you haven't. It's all good. But examples of like what these models could be used for in terms of image classification is like recognizing digits within images. So if you're trying to create a model that can like read data or read handwriting, these models are really good for that. Another example could be if I'm trying to filter out spam emails from regular emails. There's certain patterns of how people write, for instance, that I can categorize as more likely to be spam or like more likely to not be spammed. These are examples of like applications of logistic models. But that's pretty much like the motivation. Do we got like any questions or anything? If not, I know it's a big room, but cool. All right. So let's talk about binary classifications. Let's start off slow right here. So in terms of binary classifications, I'm going to be using this example of essentially like given an inputted like images, right? We're going to see if we can categorize our inputted images as either dogs or cats. Fair enough? We good? Cool. So in this like hypothetical model where we input a dog or a cat image, it does this little fancy magic, and then like we categorize it to either be cats or dogs. Let's take a look at what we're inputting here. First things first, we're inputting in an image, right? What is an image? An image is an array of pixels, just a bunch of pixels, right? And you're probably seeing on here, these slides, that each pixel is a feature. What is a feature again? A feature is essentially like a trait, maybe like in our case, a trait of maybe a cat or a dog that within our model tells our model like, hey, I think like this is like kind of leaning towards a cat or like kind of leaning towards a dog, right? So for instance, in this example where we're saying each pixel is a feature, maybe if we look at one pixel inside of our cat or dog image and that pixel's like gray, right? Maybe we're thinking like, oh, this is probably like leaning more towards a cat, right? Because I've never seen a gray dog before, right? So like obviously, surely this means that like we're probably dealing with a cat, right? That's an example of a feature. Is that fair? Or, cool. So considering this input, evidently with a binary classification, we're going to get one of 2 outputs. So generally these outputs are either going to be 0 or they're going to be 1. So maybe in this case, what you could do is you could say like, okay, if I get a 0, that means like, let's associate that with dogs, right? So if I throw my image into the model and it throws me a 0, that means it thinks that image that I inputted is a dog, right? And maybe you could say the same thing for cats. You can say like, oh, if it outputs a 1, then the model thinks that the image I inputted is a cat, binary classification. So given that, the idea with classification is the reason why we're spending so much time just talking about inputs and outputs is it doesn't necessarily work like that. So what I just said was a complete lie. And this is why you can only trust yourself in this cruel world. So generally how logistic models work is if it outputs 1, this is considered quote unquote yes. And 0 is considered quote unquote no. So what does that exactly mean in terms of if we're trying to categorize images and seeing if they're cats or dogs? The reality is it doesn't exactly work like that, because essentially what the model outputs is sort of like a decimal in between this range, where the maximum is 1, where we're like, yes, this is what we're looking for, and 0 is like, no, 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 right? And then if you're in between, like the model's a little confused. So when you think about 0 and 1, you want to sort of think about it sort of like the likelihood that something is true, or like how sure we are. So you don't think about necessarily in terms of our model that categorizes things and dictates whether they're cats or dogs. Don't think about it as like 0 is dogs, 1 is cats, right? Think about it sort of as like two different questions, where your first question, maybe one model is focusing on, okay, in an inputted image, how likely is it that this image is a cat? You know, where one is like, this is a cat, and 0 is like, this is not a cat. It's like a horse or something, you know? And then like maybe you have a different model that does the same thing for dogs, right? So you input an image and it'll dictate like, okay, this is definitely a dog or like not a dog, or it's like maybe a dog. It's sort of unrealistic to expect a model to output like be 100% sure or 100% like no. So the reality is we're going to get like a point like 70, point 90, and then we just sort of like based it off that from there. Is that fair enough or cool? So given that, just like what I said just earlier, so you're going to want to try and think about like what our model outputs more of as like a probability, like a percentage, you know? So if it outputs like something above 50%, we're leaning towards yes. And if it outputs something below 50%, we're leaning towards no. So if I input an image and my model detects whether it thinks like the image is a cat or not, if I get like a 0.70, then the model thinks yes. But if the model outputs like 0.2, right, it's like no, you know? That's pretty much that for binary. So what is on the agenda in terms of how we build our model? So the agenda is, in terms of our model, given an input, we want something that can predict the probability that the object essentially belongs to class 1, right? Because 1 is yes, 1 means like, yes, this is what I'm looking for, right? So let's see here. Given that, here's what we need. I don't like this slide, but it's still there. Essentially what we need, right, is a hypothesis to find this probability. And given that, we need some sort of logistic regression model in order to do all that. That entire concept that I just explained is logistic regression. Now we're going to have a model that essentially applies that logic for us, all right? So given that, let's begin working off of linear regression. This is going to be like sort of like when all the formulas begin coming in. Don't get overwhelmed by it. We're not a math class. We're not even a class. We're just a club. So like, don't worry about it. Like high level, this is a beginner's track. We're just trying to cover what's important. So let's start off with linear regression. So remember the idea we had with linear regression is we have a bunch of data and then we throw it on a graph, right? And then what our model does is it tries to find, I guess, like things that are similar between our data points, and it draws a line. And that line is essentially saying like, okay, this is what we're aiming for as a model, right? Similarly, with logistic regression, it's sort of like an extension of that kind of. So for instance, on this graph here, right, you can sort of divide it into, again, with this idea of cats and dogs, but maybe not that. Let's just focus on just cats now, all right? Either we are a cat or we're not a cat, right? So the idea with logistic regression, right, is let's say we have this chart here, like above, and let's say like above this line on the chart, these are data points, these are inputted images where we're leaning towards like, I think this is a cat, right? And then like things below the line, these are inputs where we're thinking this is probably not a cat, right? Where the further up we are, the more likely it is we're a cat. The further down we are from our line, the like more likely we think like, okay, this is not a cat, you know? The idea that we're trying to do with logistic regression is given all of these data points where we're thinking, yes, these are cats, yes, these are not cats. We're trying to see if there's like a line that we can draw, or essentially like on one side, we're leaning towards like, this is a cat. And on the other side, we're thinking like, this is probably not a cat. We're just trying to find, I guess, a model or like a formula that can draw this line that differentiates these two different things for us. Is that fair enough or cool? So given that, this is where this idea of a sigmoid function comes in. So with a linear regression, remember that linear means line, which means straight, which is not what we're looking for, right? So as you can see, I know this is crazy, but the sigmoid function is curvy. So what this essentially means, right, is we're trying again, sorry. we're trying to get a probability, remember, right? And sort of to get a probability, right? We're trying to see like what the probability that something is going to be a cat, something that isn't going to be a cat. So given this formula, what it's essentially saying is for an input X, and the notation for all of these formulas is X is always going to refer to our input, all right? So given an inputted X, right? What we're saying here is we're just sort of trying to define this logic in terms of math, okay? So given an inputted X, we're going to say if this function outputs above a 0.5, above a 50%, we're leaning towards 1. Or like we're leaning towards, yes, this is a cat. If this sigmoid function returns a negative or like a below 0.5, then this is, I guess, a mathematical way of our model telling us like, no, I don't think this is a cat, because the probability that it's going to be a cat is like less likely, if that's fair enough. So given this, oh yeah, any questions or anything? Or you don't have to understand like the formulas, but cool. All right. So given this idea of a sigmoid function where we can essentially put in some inputs and its outputs will essentially give us a probability of like how likely we think we have a cat or we don't have a cat. Given that idea, let's begin to try and build our model. And this is where all the math stuff is really going to come out. Don't be scared. Take a deep breath. Everyone take a deep breath right now. It's going to be all right. Okay. So let's start off with the model. So remember like from like 3-4 weeks ago, right? We had this idea of weights. So if you've completely forgotten what weights are, don't worry. The idea with weights is essentially for certain inputs, we want to sort of like, remember that within our model, we put in inputs to train our model to make it like better at categorizing whether things are cats or not cats, right? So for certain inputs, we want to make sure that certain inputs impact our model a lot more than other inputs, right? So if I'm trying to train my model to differentiate between cats and not cats, and I input just a regular image of a cat, I want to put a lot of weight on that, right? Because I want to say, yes, model, this is a cat. This should be impacting how you dictate what are cats and not cats from here on out, right? But if I input maybe like a photo of like an AI generated like cat dog, maybe I want to put like very little weight on that because I don't want that to like mess with the logic of my model, right? And obviously with this sigmoid function we have right here, we can't really account for that, right? Because we don't really have like weights inside of, what's up?
You're good.
Okay. We don't have, oh shoot. You're good. That makes a lot more sense. Okay. So given our sigmoid function as of now, right, we don't really have any way to account for weights, right? So how do we account for weights? We literally just multiply it in. So we still have our sigmoid function here, right? It's just on our term of X, which remember our X refers to our input, so our inputted images, or in this case, all we're changing, right, is we're multiplying X by its given weight, right? We're making sure that its input, right, it's being proportionally, it's going to proportionally affect our model however much we want. And then we're also adding this bias term because evidently, right, our model is not going to be perfect, right? It's always going to have some degree of imperfection. So this bias term, this plus b, accounts for that. So hypothetically, right, with this sigmoid, this modified sigmoid function, right, we can sort of account for, I guess, like how important our data is and how wrong our model will output or how wrong our model will be. And so hypothetically, with this like y hat on the bottom here, the little arrow is called a hat, which is like one of the few joys that math majors have, I guess. We got a y hat here. Hypothetically, still the same logic. We should have a lot more better data, right? So when you look at the sigmoid function or modified sigmoid function, it's still the same idea, right? If we get above 0.5, then we're leaning towards a cat. If we get below 0.5, we're leaning towards not a cat. Because again, these are all probabilities. This is like how this model guessing like how likely it is that our inputted image is going to be a cat or not. But hypothetically, with this modified sigmoid function, we should be able to do this a lot better, if that makes sense. Are y'all still trucking along, or cool? If y'all ever get like bored or anything, just like shout at me and then I'll do a little dance or something. I don't know. Okay. So I've been saying probability like 50 times in this. Crazy concept, right? Remember our y like hat x, that's like referring to our output of our model here, right? We can essentially set that, our output to our model, to equal like one of these probability functions. Again, you don't need to know anything about math coming into this lecture. Personally, I've never taken a probability course, so all good. But essentially, this is our way of quantifying our logic into like formulas that we can actually use mathematically, right? So what we're saying is, all we're saying is, in terms of this formula here, is this y hat is going to be the probability that the label y is 1, given the features x we have. What does that mean? If we input something, aka x, if we input an image into this model, and if we're still sticking with this like cat, not cat thing, if we input our image into this model, all this like p y equals 1 is saying, all that this p y equals 1 should represent, right, is essentially the percentage, how close we are to 1, if that makes sense. Because 1 is a cat, 0 is not. All this p whatever is saying is this is actually just sort of like a variable just for a percent. I know it's all complicated, all this like math notation, but yeah, all this is saying is just like our model will output a probability, which is, I cannot imagine what it's like being a math PhD if it's like this. I'm gonna keep it a bug. But yeah, are we all still trucking along, or cool? Okay. Anyways, moving on. So what are we getting at here? I've been saying a bunch of words here, right? So given this idea that we have this modified sigmoid function that can output probabilities, and given that our probabilities, if we say that it's above 0.5, so above 50%, that we're leaning towards yes, and if it's below 0.5 or below 50%, we're leaning towards no, right? We're going to essentially try to define a line that will divide our data between yes and no, because that's all we're doing here, right? So that in the future, all I need to do is just throw like my dot onto the graph, and if it's above the line, yes, below the line, no, right? That's all we're trying to do. We're just trying to make it so that the work we have to do in the future is a lot less, right? So given that, let's see here. I think I already said everything on this slide. I guess like the way that we are able to do this is through gradient descent, but I'll cover that in a second. That's like a huge word right now. But essentially what we're trying to do, right? Given this sigmoid function, we have all our data points on this graph. All we're trying to do is draw that line in terms of math terms, right? So last week or 2 weeks ago, we covered this idea called mean squared error, which if you've completely forgotten what that is, all good. All that this mean squared error did, we introduced this in the linear regression workshop. All the MSE, I'm just going to call it MSE. It's too long of a word. So all that the MSE did, the minimum squared error did, was for a given model and a given output, because we have this line, right? All it would do was say how wrong our model is, right? Where if we have an error of 0, that means we're perfect. This is like exactly what we want our model to output. And the further we are from 0, the more off we are from what we want our model to output, if that makes sense. And you may think like, oh, like what's a good amount of error? What's a bad amount of error? It doesn't, that's kind of a loaded question because it depends on what model you have. But in terms of logistic regression models, we can't really use this MSE idea, because remember that we're working with probabilities, right? Before, when we're working with continuous data with models that can predict house prices, right? We can actually tell how off we are, right? Maybe you check house prices 20 years ago, right? You say, okay, starting from here, predict the house prices in 10 years, right? And then you can check what your model outputted versus what the actual prices were in 10 years, right? But in terms of like, I guess like really weird models, right? In terms of like drawing, I guess, a line between like what is a cat and what isn't a cat, right? There isn't really like a line you can draw, right? This idea of MSE just doesn't work, right? Because in terms of math terms, this is just going to really mess with our data. Because what'll happen is it'll make anything that's really good super good, and anything that's really bad super bad, because it'll square it. So we'll output our probability, right? And if we have like a 1, it'll be like a 1, it'll be like 1 squared, like, wow, this is like really good data, right? But if we get like a 0.49, right, it'll be like, wow, I am so conflicted right now. Our model will, it'll just be like really extreme, right? We just want our model to draw a line. We don't want to like manipulate our probabilities, right? Because our probabilities is the essence of what makes our model like have logic, right? And we don't want to really be manipulating that much. So that's why we don't use this idea of MSEs. Basically TLDR, no MSE bad. Good. Great. Okay. So remember that 2 slides ago, we have this idea of we're trying to draw this line between what is a cat and what is not a cat. All right. Given that, one way that we can do this is through this seemingly very complicated formula here called a binary cross entropy loss. That's a big research term. Most people just call it log loss. And it looks really intimidating. Again, this is not a math class. We're not trying to be a math class. It looks really intimidating, but it's really not that bad. This is essentially the way that we can, in math terms, say that our formula either outputs a 0 or it outputs a 1. That's it. So for instance, as you can see on the left side of this equation here, we have a y hat and we have a y. So the y right here will refer to the output of our model. So the y, no hat, will either be a 0 or a 1 or some percentage, right? And then the y hat right here will refer to our input in this case, or like our prediction, or whatever you want to call it. And essentially what the idea is here, the thing that makes this formula really cool, right, is if you input a 1, half of the function will just disappear. So for instance, on the right-hand side of this formula, where you see the 1 minus y here, right, if you input something that has an output of 1, right, it'll just be 0 times the rest of that on the right, the like log 1 minus y hat, right? That thing will just entirely vanish, leaving us with only our negative log y hat term, right? And if we input a value of 0, I know this is so interesting, right, guys? If we input a value of 0, right, our left term will completely disappear, right? Because it's y times log y hat, right? That'll just, it multiplies to 0, it's gone, right? But on the right side of our equation, we still have that because it's 1 minus y. So it's like 1 times the rest of that, the log 1 minus y hat. Does everyone see that? Cool. So given this log loss function, right, where essentially like we can essentially make like a Boolean where it's either true or false, 0 or 1, whatever you want to call it. Given that, this is where, okay, big sigma, whoa, big words. Okay, break it down here. So what this log loss function does is for one single data point, right, one image we input into this model, we check if one feature, so like maybe like color, maybe like size of the animal, whatever, we check if one feature is either more likely to be like true or more likely to be false. So moving in to this cost function here, all that we're saying here, all this sigma is, the sigma sum is saying, is we take our log loss function, right? And instead of for one point, we're going to apply it to all of our points. because again, to train a model, you can't just train a model on one piece of input, right? You need like lots of inputs, right? So this is the way that we quantify that. So if I input like 100 images into this yes cat, no cat model, this is the way that we can quantify like whether our model will generally lean towards yes or generally lean towards no. So the M in this case will refer to how many pieces of data we input. Is that fair? Cool. Okay, I'm gonna get a little more complicated here. So remember that we're checking all of these points only for one feature. So in terms of a model that can detect whether we have a cat or not a cat, that we can maybe be checking like, oh, is this like image, does it have like more gray pixels because gray means cat, right? Maybe we'll have like another like aspect of this model check for like the size of the animal, right? Because we can have like a gray horse. Those don't exist, but we can have like a gray horse, maybe. Those are huge, right? But a gray cat, those are like really tiny, right? Maybe that could be another feature that our model looks for, right? This cross entropy loss function right now only checks for one feature across all of our points, okay? Oh, wait. Before that, though, loaded question. It's okay if you get it wrong. What is the correct loss function here? Haha, pop quiz, lol. Do we have any ideas? Given that a log function, if we input 1, half of the formula disappears. And if we input 0, the other half of the formula will completely disappear. Do you have any ideas? Do we have hands up for A? Hands up for B? Hands up for C? Hands up for D? Okay, everyone who raised their hands for B, you're exactly correct. Because for B, unlike the other equations, if you input 1, the entire right half of the equation will disappear because it'll multiply to 0. And if you input 0, the entire left half of the formula will disappear because it's 0, right? Anyways, back to our agenda here. Gradient descent. Whoa, whoa, whoa. Partial derivatives. Whoa. This is partial derivatives and sigmas. Like, whoa, whoa, whoa. Crazy. Again, like I said earlier, the formula that we were just working with, this one right here, our cross entropy loss, this is checking all of our data points for one feature, right? But turns out models, in order to differentiate between what is a cat and what is not a cat, you need to check a lot of different features, right? So all this formula is saying, this like xt, remember x is our input, t refers to a matrix transpose, who cares what that is? All that this gradient descent is referring to is this is our way of quantifying, I guess, like that across all of our data points, we're going to be checking multiple features, right? And the multiple features that we're going to be checking is going to be based on this y hat. This y is referring to a vector of features, a lot of math terms. Essentially, all this formula is doing right here is this is just our model, essentially. So this is going across all of our different data points, checking for all the different features that we look for in terms of differentiating between what is a cat and what is not. This is just the way we do it in math terms, and math is not pretty, so this is how it looks. But is that fair enough for everyone? Or if you have like more questions about like the actual math stuff, feel free to come down and ask later, but this is like just a beginner track. So I'm trying to keep it calm, especially for midterms week, like come on now. But if you want to learn more about like I guess like how to derive it, because the derivation is pretty snazzy, I'm not gonna lie. You can find it at this website right here. You can search it up right now. I'll give like 5 seconds, but the slides and everything is going to be like posted, so don't feel like obligated to like type it now or type everything I say like now. You know, we'll have a recording of this. We'll have everything up. Let me make sure. Okay, I'm not muted. Okay, we don't have to redo this workshop, guys. Cool. Okay, but last things last. Given this is like not related to math at all. Do we have any ideas for which one of these hypothetical situations logistic regression would work the best for? So remember that logistic regression, we're trying to categorize our data. Whereas continuous, we're trying to like quantify our data, like temperature, you know? So do we have any ideas for A? Any for B? Any for C? And any for D? Apparently the answer here is B, but you could argue, I could say you could argue for D. Essentially the idea with B is, remember this idea of like a binary model that we talked about. This is essentially just like an ideal definition of a model that could do that, if that makes sense. So it either
B is very ethically dubious. We don't condone using logistic regression to approve or deny a loan.
Yeah, for you people on the Zoom call, ACM AI does not condone unethical usage of logistic regression. See you in court. Okay. But do we have any questions or anything? Yep.
Can you do a little dance for us?
Sure. What dance do you want?
Anything.
Ooh. Ooh. That good enough for you? Okay. That's embarrassing. Okay. Okay. All right, but that's gonna be it for my portion of today's lecture. We're gonna have our other officer, Gregor, explain to you multi-class classification. But yeah. Yeah. Give it up for Gregor.
Before we get started on multi-class classification and kind of just expanding out what you've already learned to more dimensions, we're going to take about a 5-minute break. If you guys are okay with that, please use this time. Just go to the bathroom, get some water, whatever you need to do, all right?
Oh, that shit is...
All right, so just getting back into it. Now we're going to move into multi-class classification using logistic regression. Most of this section is really just going to focus on how we can expand what we've already done into higher dimensionalities. Okay, so let's start with the labels in that regard. Imagine that we have this set of images that contains a bunch of different animals, cats, dogs, chickens, ravens, so on and so forth, just a ton of different animals. And we need to label them. The naive approach that a lot of us would probably start with is simply labeling them from 0 to n, where n is the number of classes. So cats would be 0, dogs would be 1s, chickens would be 2, fish would be 3. But this kind of has an issue. Can anyone see what that potential issue is? Well, with the loss function that we've already defined, there's no real way to extrapolate out to n dimensions. We can't just add on a 2 minus y term or a 3 minus y term, because otherwise other terms wouldn't go to 0, and therefore our loss would be difficult, if not impossible, to work with in that situation. So instead, we're going to do something called one-hot encoding. For each image, we're going to assign a 0 or a 1 to each category, depending on whether or not the image is under that category. So for example, with the cat, the label would be in the first index, or 0, and would be given a value of 1, whereas for all other indices, it would be given a label of 0. We then put these labels into a vector indexed by each class and attach each one to an example. To be clear, this can also be used as a data cleaning methodology in the case that you have categorical data. It's not just limited to the labels that we're going to be using. So now that our samples all have one-hot encoded labels, our model needs to be similarly shaped output so that we can compare our predictions and our labels. So now we must move into expanding the model. Now for a binary model, we have a single training example X as an n-dimensional vector for the n features of the example. The weight vector is an n-dimensional column vector, and the bias B was a singular real number. In the multi-class model, we have the same input X, but we're going to be expanding the weight vector and our bias vector. So now the weights are an n by c matrix, where c is the number of classes and n is the number of features, and our bias b becomes a c-dimensional vector. Now, just to run through what this will look like, for our animal example, to generate the output, we'll take the pictures and pixel values associated with each of them and put them into our vector for x, just as we did with the binary classification. We now then multiply it by our weight matrix transposed and add the bias vector. And then finally, from that operation, we'll have our prediction z. Now, one of the things you might notice about z here is that the numbers are not really close to 1. Some of them are large, like 23 or 34, and some of them are small, like 1 or 9. What this kind of represents is where the model thinks this should be classified, but not giving it a distinct label. Quick poll before we move into our next segment. In multi-class classification, with F features, C classes, and M training samples for X, the matrix W, our weights, will have the dimensions of A, F, and 1, B, F, and C, D, M, and F, and D, C, and M. Who here thinks it's A? Who here thinks it's B? Who here thinks it's C? And who here thinks it's D? Well, you all got it right. It'll be an F by C dimensional matrix. Again, does anyone have any quick questions before we move on? Anything that you're getting confused by? Cool. So that's going to lead us into the softmax section. In the binary example, we used a sigmoid function to create a probability distribution of our labels. In the multi-class case, we generate an extension of that in order to create a set of probabilities from our output. So the softmax function will take in the output vector z from our model and output the vector y hat of probabilities for each class that sums to 0. To convert our outputs to z to probabilities, we will raise e by the component of our output vector z and divide by the sum of previous vector to get a vector of probabilities y hat. Does this kind of make sense to everyone? Does it make sense why we're doing this? Cool. So why are we using E in softmax? Why not try and create that simple ratio? Why not just take the sum of values? Well, the exponent's always positive and it's monotonically increasing, and it empirically works well in multi-class classification. I'm not gonna lie, I don't know what monotonically increasing means.
Monotonically increasing is basically the derivative is.
There's your answer. Again, don't major in math.
But I think everyone here knows what the derivative is.
Basically, for all time, E will be increasing. So now that we've kind of gone through expanding the model outwards and into this new case where we have multiple classes, we need to redefine our cost function in order to properly serve our gradient descent. To do that, we'll be using cross entropy. We need a general loss function that can apply to C number of classes, and it needs to have a higher cost if our model makes a bad prediction, or the probability of the correct class is far away from 1. This function is called cross entropy or categorical cross entropy. In this function, we're going to take the predicted vector and the actual vector as inputs, and then sum the negative yi, which is the ith element of the ground truth vector, multiplied with the log of y hat I, which is again the ith element of the predicted vector. The only class that will contribute to the loss is the class that has a 1 in the label. To minimize the cost, the model needs to make the corresponding class in y hat as close to 1 as possible. So now that we have that defined, our total cost across all training examples becomes 1 over m times the sum of the losses over each example, which expands out into this formula on the bottom here. Now that we've defined cost, we can move into really quickly discussing how gradient descent will work. The derivatives are the same as those in binary classification. It's basically true because softmax acts as a generalization of the sigmoid function, and cross-entropy loss is a generalization of binary cross-entropy loss. So in short, with multi-class classification, you really just need to understand single binary classification, and then the math is largely the same. So now we're going to put it all together. We'll take the input pixels, input it into our linear model, and apply the softmax function, giving us these probabilities. And then we'll take the cross entropy loss, which will be 0.61. So find a little quick poll. Your model outputs the following probabilities for multi-class classification with 5 classes. If the entries on the vector are 0.3, 0.2, 0.3, 0.1, and x, what is x? So who thinks it is A, 0.3? B, 0.2? C, 0.5? Or D, 0.1? Cool. It is going to be D, or 0.1. So now that we've kind of gone over the methods and a lot of math that you don't really need to remember, let's talk a little bit about ethics and where multi-class classification and logistic regression can come in decision-making. So for a long time, we've had the question of how can we incorporate ethics into AI models and robotics? In the 20th century, the science fiction author Asimov wrote 3 laws. A robot cannot injure a human being or through an action allow a human to be harmed, which is the first law. A robot must listen to humans unless it goes in conflict with the first law, which is the second law. And then the third law is a robot can protect its existence as long as it doesn't conflict with the first 2. Recently, in 2014, the MIT Media Lab conducted an experiment to kind of give an understanding of the ethics that we all hold on average across the country. Given different scenarios, including a self-driving car, and prompts, the user is to choose which of the 2 scenarios would be the lesser of 2 evils, of which scenario would be more morally correct in their opinion. So say a self-driving car is driving down the street, and there's an elderly person in the crosswalk and a young child on the sidewalk. Which would be best for the car to take out if it had no other choice? That is the kind of scenarios that we're given. And that essentially is the only way we have of quantifying our ethics, is just asking the wide variety of people in the country what they think is best in a given scenario. So now we're going to move into a Python tutorial taught by Jackson.
Yes, alrighty. So,
and really quickly, our attendance code, if we haven't already mentioned it, is it's a bird.
next week's not logistic regression.
Next week is not logistic regression.
Don't worry about it. So if we alrighty. So now we're going to be doing a quick little code demonstration, implementing in practice what we're talking about. Now, as you guys probably remember, there was a ton of math up there, right? And you might be wondering, like, hey, is there like is there anything that we can like do to like not have to do that math? And the answer is yes. And we are going to be using some machine learning libraries. This is actually the topic of next week's workshop. So, you're not going to fully understand everything that's going on here. There's going to be a lot of hand waving, me just sort of being like, it just works this way. Don't worry too much about it. Because again, this is stuff that we're going to be going over next week. But for our tutorial today, the first thing we need to do is import a bunch of libraries. So yeah, run anyway, trust it. As you can see, there's a bunch of libraries listed up there. There's NumPy, there's Matplotlib, there's sklearn, and those are all relatively standard machine learning and like data science libraries that you'll see used a lot in Python. And basically what we have to do is actually load them in and be like, hey, by the way, Python, we're going to be using NumPy and we're going to be using sklearn because it won't do that for us otherwise. Now, there is from sklearn, they provide a lot of data sets to us, one of which being the iris data set. So instead of having to like actually go out and collect our own data, because we're just, practicing, we are going to be using the data set that they provide us, right? So we're going to load the data set into the X and the Y variables. And then as you can see here, we can see what the shape of those are. Now, when we call shape, this is one of the things that we'll talk about in more detail when we go over the machine learning libraries. But when we're calling shape on a NumPy array like that, it's going to output the dimensions of that array, right? So if it says X has shape 154, it's basically just a 150 by 4 matrix. And then if you see this notation where there's nothing here, that just means it's one-dimensional. Now, any questions so far? Alrighty, so the Y has a shape of just 150. The X has a shape of 150 by 4. Does anyone have any guesses for me as to which one contains the label and which one contains the features? Because one of these, X or Y, is going to contain, a list of what each individual data point is, right? We're classifying irises, which are a sort of flower, and we're saying it's one of these 3 classes of irises. And for the other, we are going to be storing all of the relevant features that we're looking at. So using what we've learned so far in this workshop, anyone have any guesses, X or Y? You have a 50% chance of being right. So no gamblers, I guess. Oh, all right. I guess no sports bettors here. So if you look up here, we can see that Y is going to be a 150 by 1 shape, which makes a lot more sense for anyone want to say? Close, for storing the labels, right? Because if we have like a 150 by 1 matrix is really just a long array, right? So it's just a long list, right? And if you're storing a list of what each data point is, you would probably want to just use like, a normal list with one dimension, right? Versus a 150 by 4 array is going to be 150. You can think about it in like programming terms. It's like a list of 150 elements, and each one of those elements has 4 points, right? Now that is not necessarily what we want to be using if we're using that for classification. We could use that if we're doing some kind of encoding, right? But for our purposes, we are not doing an encoding, so we're going to be using that for the features. Now, one last question. If it's a 150 by 4 array and there's 150 data points, how many features does each data point have? Close. So there's 150 data points, right? And so the 150 here is referring to the fact that for each data point, we're going to need 4 features that we have loaded in here, right? Now, what we're going to do here is we're just going to drop the last 2 features. Now, in practice, you wouldn't do this because more data is usually better. But for our purposes, we want to be able to graph it in 2 dimensions. So we're going to drop it. And as you'll see, we'll still be able to do a pretty good job of guesstimating which iris it is. Now, if we run this, we'll see that X now is a shape of 150 by 2. which basically means that instead of the 4 features from earlier, we have how many? 2. Beautiful. Now we have one last step that we're going to take, because there's 3 sorts of irises in this data set that we're classifying, right? 3 different sorts of flowers that we want to be able to tell apart. But we want to start off with an easier question of just telling 2 flowers apart, right? So what we're going to do is we're going to write this function called convert to binary, and it's basically going to convert to every single data point that has a value of 2, we're going to drop, because the labels are 0, 1, and 2. So there's like the 0th type of iris. I'm not actually sure what it corresponds to, but like 0 corresponds to one type of iris, 2 corresponds to another type of iris, and 1 corresponds to another one. That makes sense to everybody? The blank stares I'm gonna take as a yes. So what we're doing here gets rid of everything with a 2. So now we only have to worry about saying, is this a 0 or a 1, instead of saying, is this a 0, a 1, or a 2? Because if you guys remember, the multi-class classification was a little bit more complicated than just classifying between one of 2 things, right? So, and then this notation up here, you might be looking at that and be saying, wait, like this, if you have some Python knowledge, you might be like, is this going to work? Like we're saying y is not equal to 2. Wouldn't that just evaluate to a Boolean of like true or false? And normally it would, but this is one of the fancy features of one of the data science libraries we're using called NumPy, where essentially if you write something like y is not equal to 2, it's not going to output a Boolean, but instead it's going to evaluate every single y value and see if it's equal to 2. And if it is, it's going to return false. And if it's not, it's going to return 1. So we're basically getting a big array where it's telling us which locations in this array are 2s. So I know that was a lot, but basically you don't need to worry about how it works. It just gets rid of all the 2s for us. Everyone on board? Beautiful. So we're going to just function. And then as you can see, after we convert it to binary, it now has shape 102 and 100, because now instead of 150 data points, we have how many? 100. Beautiful, right? And that like kind of tracks, because this means that we have, presumably 50 of each data point. So if we're converting it from 3 types to 2, we'd probably see a 2/3 decrease. So now this is just a function that we wrote to plot the data. Do you guys want me to go over what like each step is doing? It's not super relevant to like actually like the logistic regression part, but if there is interest, I'm happy to do so. Anyone have strong feelings? Anyone a big fan of learning about how matplotlib works? All right, I guess you guys are pure data scientists. No interest in how this is working. But so as you can see, we're going to go ahead and plot the data up here. Also, I don't know if I mentioned, but you can make a copy of this on your own, and sort of like if you do that, that means you can like make changes and like save them and like see what, I don't know, maybe you want to try and classify it with more than 2 features, right? And see like what that looks like and how that changes your data and stuff like that. But anyway, so we have the plot data. And so we can see if we're trying to classify between the 2 classes, there's a pretty good split right there. And so hopefully we'll be able to come up with a relatively decent classifier, because these are 2 relatively distinct groups, right? Now, what we're going to do next is we are going to split the data into training data and testing data, right? So again, this is a built-in function from one of the libraries that we imported that is going to split it into both training data and testing data for us. Does anyone remember why we need to do this? No one? Anyone have any guesses as to why it might be important for us to split the training and testing data? Because you might be thinking to yourself right now, why do we need separate data to train on than to test on? Can't we just train it on all the data to make it better and then test it on all the data to see how well it performs? Yes, exactly. Right. Essentially, when you're training it, and like this is not just for logistic regression, but this is for machine learning in general. But if you have your training data and your testing data overlap, right? When you are training on the data, it's going to be really good at like, predicting or whatever it is you're trying to do with that data on specifically that data, because that's like what it's being trained on, Like if I trained you on like 500 pictures like of cats and dogs, you would get really good at recognizing cats and dogs in general, probably, right? But even better, you would be really good at recognizing specific pictures, right? Because like if I trained you enough, you would be like, oh, there's a sandwich in the background. I know for a fact this one's a cat. Like I don't even need to look, right? And so it's a similar idea here, where if you are training on a bunch of data and then you test on that same data, you're probably going to be much better on the data that you trained on, because that's like what you're being told to do. You're being told to get really good at making predictions based off of this set of the data, which, is great and all, but we want to know how well does this generalize. We really don't care how well our logistic regression is going to work on just this training data, right? Because we already have like this data classified, like that's fine. We want to know how well this is going to perform when we give it new data that it's never seen before, right? Because, probably what we want is a line that is going to go like somewhat straight, like through here between the two classes, right? But what could happen is we could have a situation where instead it's like, okay, if it's anywhere in like this exact blob and like traces like this outline, then I know it's class 0. If it's anywhere in like this exact blob, it'll be like class 1, right? I mean, like that's not really what happened behind the scenes, but it could vastly overfit to the data, which is another term that is very common in machine learning. And we would have no way of telling, right? Because we'd be like, okay, we trained it on all this data, when we tested it on the same data, it's doing wonderful. Okay, this is great to deploy. And then we put it out in the real world, and I don't know, all of a sudden it starts telling us, misclassifying irises, or I don't know, telling us that a cat is a dog. So, and that's something that we don't want. That makes sense to everyone? Any questions so far? Not just about training versus testing data, but just about everything? Good. All right. Wonderful. So once we've split the data, this is the very handy thing. Remember all that math that we had you guys look at on the slides and it kind of gave you a headache? Well, we're done with that. Not really, but we don't have to actually code all that math in, because logistic regression is a pretty common thing to do. So, one day some people got together and they're like, hey, let's make it so we don't have to manually code logistic regression, and make it so we just have to do it once, right? And so this is going to fit the logistic regression on our training data, right? And then we are going to print the accuracy that we get on the test data. And why would we print the accuracy on the test data and not on the training data? Come on, guys. This is what I just went over. Yes. Yes, exactly, right? We already know that it's going to be like pretty damn good on the training data, right? We don't care about that. We want to see how well it does on this other data that it's never seen before, and see if we can't like surprise it. But as we can see here, we're doing pretty good. Test accuracy of 0.95. So that means roughly, and again, this is a very small data set, so we can't really, if you really did this, you want a much larger data set, but roughly it's around 95% accuracy as far as we can tell. That's pretty good, right? Now, we are going to get the model weights, right? This is going to get us the coefficients, and that's if you just call the coefficients property of the binary model, we will see what its coefficients are, and we can see here that it's 2.706 blah 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 negative 2.9753 blah 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 blah, right? And so those, if you remember from the presentation, there were two coefficients that we were trying to fit in the sigmoid function that we're modeling, right? So, and then we can also do the same thing with the bias, except instead of coefficient, we're going to call intercept. And so finally, what we're doing up here is we're just plotting the decision boundary of the model, right? So this line is telling us, hey, we think based off of, our training that like this is the line between the two classes, that if it's on this side of the line, it's class 0. If it's on this side of the line, it's class 1. And as we can see, we did a pretty good job of deciding on that line. So any questions about anything we did here with our binary classification? Or jokes? Okay, well, I guess no one has any good jokes. So now that we've done binary classification, give it up for yourselves. Woo! We're going to tackle a little multi-class classification. So, remember what I was saying before about we are at first going to only be looking at 2 classes, right? Class 0 and class 1, just to make it a little bit easier for ourselves. But then later on, we are going to be doing a little bit more classification here, which as we can see, we are plotting the data and see, okay, so now it's a little bit more complicated, right? There isn't just like a line that we can run here that's going to neatly like separate these guys. We're going to need a little bit more robust of a relationship, right? So now again, we are going to split our data into training data and testing data, which you guys all perfectly understand. You guys are pros. And again, we are going to just call the built-in logistic regression fit function. Now we're going to test the accuracy again. Again, we're doing pretty decent, right? We have about 93-ish% accuracy on our model, and that's pretty good. And then if we get our parameters, we can see that we get the model weights and the model bias, right? Now, who can tell me why? So this for the weights is a 2x3 matrix, right? And this for the bias is just a one-dimensional matrix of length 3, right? So who can tell me why the weights have this dimension up here? Why is it that we have these 3 rows of 2 and not, I don't know, 4 rows of 2 or 3 rows of 1? Any guesses? Yes. Beautiful. You nailed it. Nailed it. No. So just in case anyone didn't hear them, we have 3 different classes, right? We're trying to classify as class 0, class 1, and class 2. And we're doing that based off of 2 features, right? And that's, exactly how we get these dimensions, because for each of the 3 classes, we are going to weight the features differently, right? So this is like class 0, we're weighting, the first feature by negative 2.5, and then the second feature is being weighted by like 2.1, right? Or if for the second class, though, we weight the first feature much differently, right? Instead of negative 2.5, it's about 0.6, and so on and so forth. Now, who knows why the bias is the dimensions that it is? Because, I mean, I don't know, like this isn't the same dimensions as the weights. Why is that? Why do we have 3 biases instead of like, I don't know, again, another like 3 rows of 2? Did I hear someone say something? Any guesses? No guesses? I mean, what do we know about the number like 3? The number of classes, right? So each class has its own unique bias that we're adding onto it. Because if you remember, the bias is like the slope intercept, like it's just a number that you're adding on. So each class gets their own bias at the very end. It's our way of like correcting and just adding on. But we're not actually, we don't need any more than 1 per class. So everyone at least pretend that they understand the, dimensions of the vectors and stuff like that. Yes.
Maybe it's just like the bias, maybe the column vector rather than a row vector.
Yes, it would be a column vector. It's just because of how it's getting printed out. It's like the actual, let's see. As you see, where is it? As you see here, right? It's not 4 4 columns, it's 4 rows. But just by nature of how these are printed out, and they're just treated like one-dimensional. It's not, you know, you don't have to worry about it. But very, very good catch. That is exactly right. It is actually 1 column vector instead of a row vector. But anything else? No? All righty. So now we're finally going to visualize our results. And so we can see here, okay, we did pretty decent, right? We did really good, in fact, with class 0. Class 2 and class 1, though, were a little bit harder for us to differentiate, right? You know, you can see we pretty much got every single class 0 right. But then for class 1 and class 2, you know, it was a little bit of a crapshoot. We did get a decent number of those guys wrong, right? Now, does anyone, so it looks to me like maybe our accuracy like wasn't quite there, but you know, who's to say? Does anyone have any like potential reasons why our accuracy, you know, might not be 100% reflective of our true accuracy up there? No. Well, it's really a problem with a very small sample size and not a lot of data, right? If we're taking like, I don't know, 20% of 150 data points, right? That's only 30 data points. And like, we're only training this on 150 data points total. So we're not going to, there's a good chance that we like don't get things very robust. Like maybe our 30 data points are like mostly of class 0, right? Like if I showed you this model and then like, I don't know, I picked out a bunch of random ones, but happened to choose like, you know, a handful from like, that's like mostly from class 0 and then like fewer from, you know, class 1, 2, you would probably get like a skewed idea of how accurate my model is, right? And so there's that consideration there. And then we also see that this is a very complicated like interaction and a little bit harder for us to sort of extract class 2 from class 1. Does anyone have any ideas how we might be able to better separate the two using our logistic regression model? And I'll give you a hint. It's not really anything that we can accomplish right now with our setup as it is. Adding more features, right? So there's a wonderful idea right there. If you guys remember, we had 4 features and then we lopped off 2 of them. So if we have 4 features instead of 2, that's doubling the number of features. We can probably do a pretty good job of classifying, or at least a little bit better than we are right now, if we're looking at more features of the data we have, right? So there's a really good idea. Anyone have any other thoughts about how we might go about improving this model? More data, beautiful, right? Like I said, we only have 150 data points. Like that's, I mean, 150 is a lot, but it's not that many, you know? And so as we get more and more data and get more and more data and like the volume of data and then more and more detailed data, meaning like, you know, more features and stuff like that, we're going to be able to improve our models. So yeah, that's everything that we had. Next week is not logistic regression. I'm going to change it to libraries. But yeah, as always, feedback form is up there. If you're doing the attendance code stuff, the attendance code is up there. Next week, we'll be going over ML libraries. If you had any questions about you know, any of the concepts we went over, Eric and I will be up here for a little bit longer. Yeah, but thank you guys all for coming. Hope you had a wonderful night.
Good luck on your midterm.
Yeah, good luck on midterm.